Hey, welcome back. Let me check the stream settings, make sure that we are live, we have sound, should be up and running. Here we go, live, we have sound, should be up and running. Looks good to me. Cool. Okay, so we're taking a look at homework 2 in this video. There was a lot of great work that I saw kind of looking at like how to pre-process data, how to work on things. One thing that I wanted to point out with this bubble plot was, I won't go through and do everything. So I saw like some scatter plots and then like this style bubble plot, but if you keep coming down, there's some code to actually make it like a nice color, like add different colors and different sizes for like each size has to do with how many beers were in that style, and then even labeling ones, like this one says like if there's more than 65 show that one. So this is a better plot in terms of like a bubble plot, like actually representing this data. Some people flipped the ABV and the IBU axis. That's fine, like there's no reason not to. But then if you do that, make sure that you're also replotting this pre-processing when you remove all those NA values rather than filling them with zeros. So that's the main difference there. So I didn't want to go through all of this because all the code is kind of here, and you can grab it kind of one at a time. And at least one way to do this is you can try running it and just one at a time of like, okay, well, style means is not defined, so we'll scroll back up and grab the style up. Grab the place where style means is created. So I can grab that one, but then it says beer styles is not defined, so I can go back up and find like beer styles and copy this one in. And then beers clean is not defined, so I can come back up. So anyway, that's kind of the general process. At least if you're trying to reproduce someone else's plot like this, you can go through one by one and build things in there. One thing I did want to take a look at was, and actually usually people have trouble with creating this, coloring the data according to designer, but maybe through like videos or through help, that it seemed like it was easier to do this round, that people were able to do that. So here, let's pd.read CSV, and I think it's transistor data. So I'm using tab to autocomplete. I always do that because I end up messing up what the labels are for each thing. So let's try this, TRAN. And then it prints out all this stuff. If this doesn't, so a lot of times I go to read the CSV into Python, either as a pandas data frame or as a NumPy array, and it just doesn't work. So that's why I have you run this command first, so that you can see what's here and what it's supposed to look like when it comes out as a pandas data set. All right, so plt.plot of, let's do a semi-log y of data date, and again, use autocomplete as you start. Oh yeah, not data, tran. Use autocomplete, and then TRAN of MOS transistor count. And to make it a scatter plot, we just need to give it some kind of shape. And this is kind of what this is supposed to look like. And it seemed like most people didn't have any trouble, but this was, let's call it like Trandez and Trandez like this. Here, let's do this first. If I look at all the designers in this data set, most people, what they had done was figure out like, oh, we can grab just the unique designers. And how many are there? There are 37 different designers in this data set. So I can say that designers, if I could spell, is this, and then I could say for des in designers. And what I'm doing here is saying that I only want the rows where this is true. So if it happens to be, so in the very first one, if the row has designer equals Garrett AI research, then it'll create Trandez and then create a semi-log plot of just that one. So that's to start. Oh, that would make more sense, right? Use the whole data set, not just the piece of the data set. And then I get a nice like multicolored plot. The next step is keeping track of which one is which. And by just keeping, now they are all labeled, but I need to actually display the labels. And default doesn't look great. It just like plops it right there where I'm not sure why that's the default behavior for a big long list like this, but there's some ways that we can fix it. Here, let's go into Copilot again. I gotta sign back in. Come on, let me back in. And we want module 2, learn about a topic. I need to move the legend outside the plot and add 3 column and use 3 columns in matplotlib. Let's see if this helps us at all. There we go. I don't know why it's saying location upper center and this bbox to anchor, because the bbox to anchor is a manual process, but let's just copy it all over. So we'll comment that one, add the legend here. That's not bad. So it moves it down below and it looks pretty good. So now I've got the legend there. So what this one did was that negative 0.1 is throwing it down there, and then the 0.5. Actually, what does that do? Oh, halfway. Halfway, maybe the center is halfway. I don't know. Sometimes I get pretty confused with this. But this one, I don't think you need that upper center. Oh, yeah, I guess you do. Weird. Okay. Okay, so that works. It's a nice way of kind of organizing it. It might bother you that there are multiple blue things. There's ways that you can fix that. We could start changing both the symbol and the color, and that would be a good way to do it. We could even ask, like, I need a list of 8 symbols and 10 colors for matplotlib. I need a Python list of 8 symbols. I need, well, let's say 2 Python lists. Eight symbols, 10 colors for matplotlib. So now I've got like symbols and colors, right? And this is a nice way to kind of mix AI and kind of human coding. Because for AI, like this was very quick. Meanwhile, if I were to type this out, it doesn't take too long, but I would have to look up in the direction of the. And now let's go. What do we want to do? So we've got 1, 2, 3. Oh yeah, we had 10 and 8, right? 8 symbols, 10 colors. CI equals 0. SI equals 0. And we'll say, oh, we can do symbol I here. We'll say symbols of SI, color, I think we say C equals colors bracket CI. And let's just see if they all end up as the same. Yeah, so they're all blue circles. Now I can start changing them. So first thing, I could just say like change the color each time. Oh, and then I want to iterate it. Oh yeah. So we'll say %10 or 11. I think 10. And do I just want to keep changing the symbols like that? And now I've got like different colors and symbols. I don't love this teal color. It's hard for me to see it, but anyway, it's making progress, right? So these Intel, they've been doing work for a long time, and then meanwhile IBM, they came along in the 80s and then did a bunch of work 2000s. So anyway, that's one way. Now, one of the big things that I saw that in the homework was anytime you make a prediction, like make a fit, you have to plot that fit with the data. It's bare minimum. Like there are other ways that you can kind of justify that yes, this fit is the right fit, but really to me, like the data and the fit are the best way. So in this case, I'm just going to look at like the US, so I'm not doing everything over and over. So US is energy of energy. Ooh. And I think it is, yeah, entity. And I think I write out United States like this. Let's double check that worked. And yeah, sure enough, I have United States from 1965 all the way to 2018. And there's how much energy we used as a country in each year. Okay, so now let's take a look at what that looks like. And we go year on the x-axis and the primary energy consumption on the y-axis. And yeah, do I want to do some squares? I like squares. So at least to me, this does not look like a straight line, but I can find a straight line, kind of what it was the average trend here. So let's do that. So my XI values are going to be US year. My YI are going to be US of primary energy consumption. My fit is a polyfit of XI, YI, order 1. And then I'm going to plot my XI and a poly val of XI. And actually, I think I say US fit and then XI. We'll find out in a second. Okay, that worked. So you give it the fit parameters and then you give it the values of that. And let's take a look at what this thing is. So when I do a fit, I get two numbers, and it goes from highest order to lowest order. So the highest order thing is the slope of the line is 200 terawatt hours per year. And then this is the intercept that in the year 0, we were using negative 0.4 million terawatt hours, which doesn't make much sense really, since Industrial Revolution would be the earliest we'd really wanting to use. The nice part about using like polyfit and polyval is I could change this. I can make it a fourth order polynomial. Excuse me. It definitely reduces the error. Like the lines get closer to the dots. That's a good thing. The bad thing is that when really the whole point of making a fit is either to interpolate, like find something that happened in between these years, and really for that we would just use some interpolation between these two data points, or extrapolate like what's happening in the year 2025. So with a fourth order prediction, let's just change this xi, change it to x, right? Say x is np.linspace from 1965 to 2025. And now we can see with this fourth order fit, it's swinging way down, which is probably not true. With a fifth order fit, it swings way up. Maybe that's more true. I don't know. But that's the main danger of using higher order polynomials. The fit is going to keep getting better and better. So the bigger the polynomial, the more data it's going to go through, but also the more unstable. Here it's even telling us like, dude, what are you even doing here? These are the pink, this like red or pink labels. Those aren't errors, they're just warnings. So it gave you a result, but just be warned, it's probably not what you think it is. Anyway, so we're just doing a first order fit. Always, always, always show that fit. And again, there's other ways that you can tell. So then the next step would be splitting this data. So maybe I think like, all right, since the 1980s, there's been a different trend than this first like 60s and 60s through the 80s, right? Like maybe 1980, something happened, and there should be a different trend here. So let's just we'll grab this whole thing, paste it down. So now I have two versions of the same thing. And let's do this. US fit 01, and then US fit 02. This is going to be when XI is less than 1980, and then this is going to be XI less than 1980. This one is going to be XI more than or equal to 1980, and this is going to be XI more than or equal to 1980. You might be looking at this thinking like, well, why is he using XI in both of these cases? And really what I'm doing here is called Boolean indexing, where I'm creating a whole bunch of true false statements. So I'm creating a new XI less than 1980. So I get a whole bunch of trues and then a whole bunch of falses. So when I ask for what was XI when XI is less than 1980, I only get these values that are less than 1980. And when I ask for YI, I get all the energy values that were true in that case. And here it's still using a pandas data frame. So I have a fit 1 and I have a fit 2, and should I use 2 of these? Let's do that. I'm just using the same kind of logic here. Oh, and it would help if I used fit 2 in that second case. Okay, so in this first one, slope is a little higher, and 01. Let's just look at the slopes for the two of them. So here, high slope, and then here, slope decreases, but it's still increasing along that. It's disconnected because the fits that we did don't have any connection to each other. We'll look at this again for linear algebra methods in Module 4 and figure out how can we connect those 2 points, like if we think there should be a connection there. But now I do have, so it was 500 terawatt hours per year. Now it's down to 200 terawatt hours per year in the last kind of 30 years since the 1980s. You could argue that it went back to normal through the 90s and maybe it decreased a lot, like maybe we've been doing more work these days. But again, always plot this on the same curve. And for the prediction, if I'm trying to predict, like, if I want to know, like, what is this value, I have this polyval, right? I can ask for 2025, and it tells me 44,087. And that's the US 01. Yeah, I'm like, that can't be right. There we go. 02 is 29,000. That sounds a little more reasonable. And so one thing here about like comparing to Gordon Moore's prediction, I saw some people kind of report like, okay, that it doubles every 2.03 years. That's really close. Like, well, how close is that? If if it's doubling every 2.03 years, like is that just uncertainty in your fit? Like it's like, why do you say that that's really close? So that was the main thing that I saw missing here, was like when people did this fit on here. I'm coming back up to this. So taking the best fit through this curve, through all these data points, end up with doubling maybe every 2.04 or 2.03 years rather than every 2 years doubling. And some people said that that's really close. But you could also say like, oh, well, that's wrong. Like he said every 2 years, but it wasn't. And the reality is that no one's going to get it perfectly right. Like there's got to be some error. Like reality has to be somewhat different. And the measured result is never going to be exactly what you said it was. But like, let's say we remove all these points that don't lie along this curve. Like maybe these were like retro computers made. I don't know what the deal was with it's not Apple, that would be Offet Enterprises down here. I don't know why they created those, but maybe we don't want to include those. And what's that red star? Acorn. Like maybe you want to drop those Acorn values too, because for the most part they weren't doing that. So maybe if we only considered Intel and IBM, it would be more like it doubles every 1.95 years. But anyway, if you're going to say it's close, just say how close it is rather than saying it's really close. It's like it's off by whatever. 0.03 is 0.3 of a year, so it's off by 10 days. Is that right? Or no, it's off by a month. Anyway, 0.3. So a tenth is 3 days, 9 days. So it's off by a week. Okay, so now we're getting into some Monte Carlo. So first 3 readings were kind of like using data that's given to you, and now thinking about like if you know something about the data, either in this case we have uniformly random, like if you're dropping needles onto a grid, they're going to land in random locations. There's no kind of rhyme or reason. So we know they're random, and we can say something about like how those orientations would help us calculate pi, kind of roughly like a circle. They carve out their probability of landing, carves out a circle, and whether or not that circle is crossing each of these lines is going to tell us something about like the area or the diameter and the radius, right? Or in this case, we know something about the manufacturing process. Like we know the size and the tolerances on our thing, so we want to propagate that error into the rest of our data, figuring out like, well, is this thing going to fail? And then then we had a random walk here, and yeah, I don't know why it joined these two, but you can split here. If we say like cell or edit, sorry, you can split the cell, and there's also that control shift minus. I don't know if that bothers everyone else as much as me, but split the cell, add a new cell below. Maybe it doesn't bother anybody else. Okay, so this one, main thing that I saw here was as you're generating these locations to check whether or not they're crossing, you have to consider both cases, whether oh yeah, I got this thing. So if you have kind of like a oh yeah, let's do this. We'll call this one R, and this one L, and now I'll grab it. So if you land and you're anywhere from like 0 to 90, or even 90 to 270, or kind of 0 to 270, or 360 to 270, anything in quadrant 1 or 2, left and right are always exactly where you'd expect them. And let's get rid of that one. It's bugging me. But you could have a case where you're over here at 150 degrees, and now what you called the left is actually on the right, and what you called the right is now actually over there on the left. And same thing over here, like anywhere up to 270. So that was the main thing that I saw in this case. Yeah, I guess this would work better, right? So there's different ways. You can either take a look at this and say, okay, make sure the left is always min, make sure right is always max, and that just kind of flips it. Or you could use two sets of logical and, or a logical and a logical or, like a combination of ands and ors. Like a... and so what I wanted to do here was, it seemed like people were getting some help from Copilot in this case. So I wanted to troubleshoot just saying like, okay, here, learning coach, tell me how to do this, and let's go through and see what happens. So it's telling me the information that I already had, creating 100 samples, and it seems to be doing this, like it's creating. So this is the old way of doing things. So let's copy this over because it should work. I don't need to import NumPy here. I already did that. And really what I want to do is, instead of importing NumPy, it's like from NumPy dot default. All right, ran. I like to use a seed. It doesn't change what the result, I mean, it changes what the results are, but it doesn't change like a Monte Carlo method. Like using a seed is just, it's kind of like shuffling, like if you're dealing cards for a Monte Carlo, like an ace is a 1 and a 2 is a 2. Setting the seed is just saying like, okay, this is one way to shuffle the cards. Like it'll always give you the same shuffled cards as you pull them off the top. Okay, so then instead of using this np.random.normal, I'm just going to say rng.normal. And let's give this a shot. Monte Carlo buckle and 200 E9. I think it's 0.01 and then 0.001. L is 5, and then N has a default value. Oh, I should set the seed, right? And sure enough, it seems to work. It deleted all of my beautiful setup, but it does seem to give us something, and I won't. So I'm setting up the Monte Carlo method, and so this one's running that. And now let's see what it's doing here. (10 to 15% of the mean. Let's get rid of that one. 160 times 0.15, 24. No, I get like 30% of the mean. Why is it saying that? I think it's trying to do some some propagation of error, but it's not really working. 7.7, 10 to the third, but that's not at all what we get, right? 160 newtons. Okay. All right, so now this one, so in the past, I think it didn't realize like that 2.5% needs to be compared to this 98.1 newtons, but this is good that the load per rod is being properly understood. So what we're doing here is that the structure is holding, these rods are holding a 1,000 kilogram structure, and if any one of them buckle, then, well, not if any one, but if multiple rods start to buckle, then they'll all start to buckle. Because then, like if one buckles, now there's only 99 rods that are holding 1,000 kilograms. And then if two buckle, then now we have 98 rods holding it. So we're trying to get to the point where only 2.5% would possibly fail. And really the way to get there is like keep increasing n, bigger is better. It doesn't change the values, it just changes each time you run this, you'll get the same. So here it's 164 and 66 almost every time. 163, 64.4. So it reduces it increases precision the bigger that value of n. And let's see. Yeah, show me the whole code for 2.5%. Let's see where it ends up. Show all the lines. And you know what, let's just copy it so we can actually run it and edit it. Monte Carlo buckle. Let's make sure it's the same. Pi cubed ER to the fourth over 16 over L squared. So what this one is doing is calculating, I want to give it some default values. I don't like the way it's ordered. So I want to say it's L, since L is the thing that I'm actually changing. This thing is 200 times 10 to the 9. This is 0.01. This is 0.001. And we can do multiple lines, make things a little more readable, and fix our typo just like this. And I'm gonna Control Shift minus. Why did it overwrite my Monte Carlo buckle? I don't want that. I want maybe I'll call this like Monte Carlo loads, right? Don't overwrite my stuff. And stop importing NumPy. Driving me crazy. All right, so if I ask for a 5 meter, so if they're all of my rods are 5 meters, they're all holding up this 1,000 kilogram structure. Each one of them has a critical buckling load. And I can look at that. What is the histogram of that 5 meter? And we have plenty. Let's make like 50 bins in here. This is the if the default I think is 10, but we have so many samples. Like I think I forget what we're up to, 10,000. So we're up to 10,000. So we could even do 100. It'll look just fine. And if I want to hide where all the bins are located, so here it is. roughly 100 newtons is what I'm looking at. There's a lot of stuff that is less than 100 newtons. And if I want to know exactly how many, Monte Carlo loads of 5 less than 98.1, and get there, np.sum. There are 1,400 rods that would fail under a 98.1 Newton load. How many is that in total? Divide by n, 14%, 14.2%. That's too many. That means like more than 10% of my rods are gonna fail, so the rest of them are all holding up. So hopefully they have like a lot higher buckling loads, but we don't know. Let's see what the rest of this thing is doing. Load per rod, n is 10,000. Better accuracy, makes sense. Bigger is better. L values. And this one, all right, so this is where I saw some try lengths from 1 to 20 and then kind of checking each one. Let's see what this one gives me. 4.26 meters. Alpha, what is this alpha times 100? Why does it convert back and forth? Why not just put this as 2.5 to begin with, right? So 2.5 percentile, because I'm not using it anywhere else. And the thing, all right, so I'm looking at here, I think it's starting at 1 and going to 20. But I don't know why it's doing this over and over. Let's just comment out this stuff. Let's see. So what I'm doing here is for each, rather than like create this loop where I'm checking if this is true, I want to see what's happening. Like it doesn't take all that long to run these calculations. Oh, I'm just going to comment that one too. And let's see this PCT 25 loads. So it starts off high and then keeps decreasing. So now I'm kind of getting a sense of for length. So as I keep decreasing the length, buckling load keeps increasing, and that 2.5%, and that kind of makes sense. Like if it's shorter, then it's probably not going to buckle. If it's really long, like a 20 meter long one, most of them are going to fail. Maybe there's some something out there that will possibly pass. Semi-log y. And now 1,000 versus 100 versus 10 newtons of like where. So we want to be right here in that 100. And this one, I guess the one thing that I don't like about like just checking each one is that really it's like right in here where we want to be. So let's go 4 to 5 to zoom in some. And it bounces up and down like we're using a Monte Carlo method. And so that 98.1, I guess we can just plot it at this point. 98.1 is up here. Like it worked at that 4.1, but then it didn't work at 4.15 or something. So what I could do is PCT loads less than 98.1. And let's look at all the PCT. Oh yeah, we want L values. Oh, because it's a list. np.array of, we can just convert it to an array. And these are all of the lengths where this was true. And here even, yeah, 5. Wait, 5? Oh wait, we want more than, right? So 4, so we want it to be higher than. That's right. Sorry, I was flipping things in my head. We want it to be higher than. So 4 works, 4.01, 02, 03, all the way up to like 4.14. And if I really, I can get more higher resolution in here if I make that smaller. I can also increase this n to try to get this wiggling down, like increase the precision of my Monte Carlo method. But again, if you're using Copilot to kind of help you get through some parts of this assignment, it will spit out an answer. But a lot of times there is no critical thinking. Like it's just giving you an answer to keep you engaged with the actual AI. So take a look at it. Like these if statements, they don't work all that great, of just like stepping through one by one. Like technically it'll give you an answer, but it's better if you're running all these calculations anyway, like plot it out. Just make a plot and figure out like, all right, well, where are the values that I want to look at? So anyway, that was one thing that I wanted to take a look at, since especially this one. This is a hard problem of like using Monte Carlo methods to propagate uncertainty and then make a design decision with it. And it seemed like that one was getting more copy-pasted code from Copilot or ChatGPT or Claude, wherever they're all like 6 of one, half dozen the other. But none of them are actually like thinking through the specifics of your problem. And again, the units are going to be way off. Like I don't even think this math is correct. 16 times 25. Oh yeah, 5 squared. I mean, it's doing like some of the math right, but this can't be right because that's not at all the answer that we got. Anyway, so some caveats. Make sure you're paying attention to like how you're using these things and where they're helpful versus not helpful. Cool. All right. Keep up the great work, and I'll catch up.